Welcome back. This is the Tutor Wizard. I'm Adrian. Please subscribe right here and hit the notification bell for all the stuff on our channel. Blah, blah, blah. Linear Algebra 1, Chapter 2 is matrices. Section 2.2 is now going to be matrix multiplication. 2.1 was 3 videos consisting of all the primary definition of what a matrix is, all these other transpose and weird operations we didn't have for numbers. And then what we also did was we gave, in the last video, we gave the structure of a vector space for the set of all m by n matrices. In particular, we defined addition of 2 matrices and scalar multiplication of a number times a matrix. Now what we're going to do specifically this lecture is matrix multiplication, where we take 2 matrices, rectangular arrays of certain sizes which have to match, which we're going to call well posed or well defined, and then we can create another matrix from 2 given matrices, but not all the time. We have to figure this out. And so what the picture is saying is always, we're going to say this differently, but the inside indices have to match and the size of the matrix is the outside indices. So if R is the number of columns in A and R is the number of rows in B, if that matches, then the size of the matrix multiplication is going to be m by n. That's just describing what the size of it. Then we have to define what the entries of all of these guys are. But these pictures are going to be essentially the definition of what matrix multiplication is. Let's get to it. Let's recall when we defined a matrix, we specifically pointed out what a row vector was and a column vector. They're going to be extremely useful. And then we said in particular that we can view matrices as a collection of m rows or n columns. And this is where it's going to start getting useful when we actually want to do this horrible matrix multiplication of 2 general sized matrices. When do we have the definition defined for multiplication? And then how do we actually do this? This is the 2 big things. So given 2 arbitrary rectangular arrays, when are we allowed to put them together to multiply them? And then if you can do that, how do you create the new multiplication matrix from the given 2 matrices that you're given? That's the problem we're about to do. And then in a second, when I show you this horrible definition, the first example we do will be to show you where the heck we got this definition from. It was not to torture first-year students. This is an extremely good and useful application, but not the driving force to how we derive these things. What we have is, first of all, before we define for an arbitrary matrix, 2 arbitrary matrices, what we're going to do is, if you're given as and the order matters, in that order, to the left, we're going to have to follow Beyonce again, because you'll see I'm going to start talking about this. When we multiply this, you can't flip it around. It's going to turn out that A times B does not equal B times A in general. So the order that we do this specifically matters. At first you didn't pay attention and you didn't want to care about whether it's order, but you can't just put C times R. That you can actually in this case, but it gives you something, it'll give you an n by n matrix, not a 1 by 1 matrix. So my point being is, if I given a row vector first and then multiplied by a column vector on the right, that is, here's the row vector and here's the column vector. And then that multiplication means that this is actually, when we do chapter 3, this will be what we call dot product. But right here, we're going to take this entry and multiply it by this entry and get that guy. And then we're going to add it to A12 times B21 and get that guy, and then dot, 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 dot. And then I'm going to take this guy, multiply it to get this guy, and then we're going to add them. So I can tell when you're doing matrix multiplication, should it be this, 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 this. This is how we're going to do matrix multiplication all the way down. And we never write it in there, but I'll write it before I erase it quickly. This is technically a 1 by 1 matrix. So how we're going to do this and how you want to pay attention already. When is matrix multiplication defined? The inside indices have to match n and n. And the size of the outcome is going to be the outside indices 1 by 1. And a 1 by 1 matrix is a number, so we usually don't write the overkill. But we have technically created, this is a number when we add it up, and that is a 1 by 1 rectangular array of numbers, which we usually call a number. Let's go further. Before we move on, let's do an example of this just to make sure we understand what's going on. And then for this one, I'll even do it backwards. Don't do it backwards. The first thing I do to solve these is, well, could you do it backwards or where would you go with this? I'll show you, but we haven't defined this in general, so I'll be cheating. I have, this is 1 row and 2 columns, and this is 2 rows and 1 column. So if they don't list it, the first thing you want to do is write down the sizes of them, because when you're doing this in general, not every 2 matrices you can put together and multiply them. They have to be well posed. Therefore, when I do this, R times C in my notation, in that order specifically, now is going to be 1, 2 multiplied by 3, negative 1, which which is now going to equal, I take corresponding entries. This is A11, so I take that entry and I multiply it by this entry, 3. And then I add, and then I take this entry, so these ones, and then these ones. So it should be 2 times -1, and that's 3 minus 2, which is 1, a number, which is technically a rectangular array, which is 1 by 1. So when I do this again, this is 1 by 2, this is 2 by 1. What I'm checking is the inside indices match, so this is well posed, and the size, and regardless when we do this in general, will be the outside indices, is the size of your outcome, the number 1. This is going to be dot product in the next chapter. What if we do it reverse? C times R. Well, that's going to be 3 -1, which is now, this is 2 by 1 times 1, 2, which is 1 by 2. Oh, and I just said it, and in general, it does. The inside indices match, but now look, the size is going to, from 2 vectors, we're going to create a row vector and a column vector. We're going to create a 2 by 2 matrix. So quickly, you haven't seen how we do this, but how are we going to do this? Each entry is going to be that row times the column. So this first entry right here will be this one times this one, 3. This entry will be this one times this one, so 6. This entry will be this one times this one, so -1. And this entry will be this one times this one, so -2. Weird. I just created a 2 by 2 matrix from a row vector and a column vector, but that's in reverse, so we don't want to do this. When you do it this way, you get a number. You do it the other way, you're going to create an n by n matrix. You don't want to be doing that. Well, later we'll do this, but for now, you want to create the number. So this is not what we were doing. You want to do R times C in that order. Good. It's still valid, but that's not what we're trying to do right now. Now let's do this one. So number 1. Now we'll do the second one. Same thing. R matrix multiplication times C. This is a row vector times a column vector. Right now, this is 1, 2, 3 multiplied by 1, 2, 1, which when you see when we're doing 1 times 1, 2 times 2, 3 times 1, this is equal to 1 times 1 plus 2 times 2 plus 3 times 1. And that's going to give me 8, a number again. Why are we doing this? This is going to be now in the general definition of what larger matrices are. Every entry in the outcome of this matrix multiplication is going to be one of these computations. Yeah, so when we multiply 2 3 by 3 matrices, we're going to have to do this 9 times to compute all of the entries. Yeah, here we go. Let's give the general definition of matrix multiplication. Okay, here it is. Definition. Let A be an M by R matrix. I'm already setting it up. We could set this. I could have rephrased this. 2 matrices are, multiplication is well posed if the number of columns in A is equal to the number of rows in B, and you're like, already I didn't like that. So there, this has to be true. The inside indices have to match. If I take an M by R matrix A and an R by N matrix B, and it has to be in that order, you can't flip them around, it won't work even. This is how we show they're not commutative. One's not even defined, and the other is, so they can't be equal. A times B, so their product or matrix multiplication. This is the third operation, not matrix addition, not scalar multiplication of a matrix times a number. Multiplying 2 rectangular arrays of certain sizes is well defined. And in that case, it creates a new matrix of a different size either than these. This is M by R, this is R by N. The outcome is M by N, the outside indices. That's what you want to memorize. And here's the drum roll. The ijth entry, Cij, is given by this hot mess. Here's the product specifically. A times B is going to be a matrix C. That matrix is in our notation from the first one in this chapter. A matrix is denoted by Cij. It's a rectangular array. Who is this entry? This entry now is, you take row I of A, you view A as a bunch of rows. That's why we wanted it. And you view B as a bunch of columns. And now I take row I in this one and column J in this one to get the ijth entry. And so Cij is row I of A multiplied by column J of B. And that was, we just saw in the other previous definition, when there was only one of them, we replace now the ones with I's and J's. And now notice that we needed the number of columns in A to match the number of rows in B, so that this inside 1 1 2 2 dot 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 RR, so that will match and we can have a well-defined multiplication to give us. Then this is, remember, if you have an N by R matrix and an R by N matrices, how many times are you doing this? A whole bunch of times. This is one entry, And remember, for an m by n matrix, there's m times n entries. So we have to do this m times n times. So if this is 3 by 2 and this is 2 by 4, we're going to have to do by 3 times 4. We're going to have to do this 12 times to get all the entries. Oh my goodness. Let's try this out at least once and see what's happening. All right, let's compute an example. We're going to do a couple examples. First of all, we'll do one where it's well posed, and then we'll do another one where I give you a few and say, you decide whether you compute these. I'll do them because it's in a video, but try to pause the video and try first and then see whether you get what I got. We should match, or at least one of us is wrong. All right, compute A times B if A, and now they start stripping everything away, so then you have to put that back in. That's specifically, we have to check this. They're just saying here's A and B and they haven't put the sizes in there specifically. I did it to myself. So immediately what am I going to do? I'm going to see whether this is well posed or whether I'm allowed to do this, and then compute it if I am. This matrix has 2 rows and 3 columns, so it's 2 by 3. This is 3 rows by 1, 2, 3, 4 columns. So this is a 2 by 3 matrix, and this is a 3 by 4 matrix. You can write it like this. Now, A is 2 by 3 times B is 3 by 4. I like to do this because why write those down if you don't even have to do any work? But this tells me I do have to do work. The inside indices are 3, and they match. Therefore, the number of columns in A, 1, 2, 3, is equal to the number of rows in B, 1, 2, 3. Those indices match. The size of C, the matrix multiplication, is going to be a 2 by 4 matrix. That helps me when you're first starting to do this, because now watch, I'm going to write this like this. I only need 2 rows. I don't need that to be too much, but then I'm going to, ooh, see, I've done this before. What we're going to do is, I know I only need 2 rows. But then I need, and that's still probably not even enough room, I'm still going to squish them in there. Once you see the computation, we now have to do the row times a column, 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 row times a column. Yeah, I just did it 8 times. Now let's actually do that. What does that say? In there, I didn't write out the matrix multiplication, so now I have to go back and do that. This says A is 2, 1, 0, 3, negative 1, 1 times B, which is 3, 1, 0, 2, 4, 0, 1, 5, negative 1, 3, 5, 2. Now what that says is this outcome. Now I'll write it very big for myself. This will be 2 rows. I know the size before I start, and that's what helps me, so I write it out ahead of time. I'm going to have 2 rows and 4 columns, so then that's what I break up for myself at first. Now what we have to do in each of those entries is, we have to do, in this entry, this is C11, this is C12, this is C13, and this is C14 is what my brain sees. And in the second row, I have to do C21 and C22 and C23 and C24. Those are the 8 entries. We have to compute how many entries? 2 times 4, 8 entries to compute this matrix of multiplication. And each of these is a row times a column multiplication. So now how do we do that? Now in each of those entries, we're going to take in the first one, we're going to use the row 1 the whole time. I'm going to do row 1 matrix multiplication by column 1, and then that will go here. And then I'm going to use row 1 and multiply it by this column, and it'll go here. And then this one times this column will go here. And then this column, or this row times this column, will go here. And then what I'm going to do is I will use that row for the second row. This times this times this will go there, this times this will go here, and this times this will go here. Now let's actually do that. In theory it's one thing, in practice it's an entirely different thing. Now we have to compute the numbers as we go as well. That's why I do this first, and then we'll write equals a 2 by 4 matrix. This is, that's the fingers. I've been doing this a long time, I still choose to use them. 2 times 3, 1 times 4, 0 times negative 1. If you want, the guy I learned from, Mark Solomonovich, just does it in head. He's like 6 and 10. It's like, okay, just write it down then. 2 times 3 plus 1 times 4 plus 0 times negative 1 is the first entry. That's what it is. And then in this one, we're still going to use the first row. For the whole row, we're going to use this vector. But now we're going to use this column. So I'm going to have 2 times 1, 1 times 0, 0 times 3. I like that one. And then in the next one, same row, but this third column now, 2 times 0 plus 1 times 1 plus 0 times 5. I like that one too. Then I'm going to use the same row and the last column for this last entry. 2 times 2, Barney math, is 4. 1 times 5 is 5. And 0 times anything is 0. Oh, she wanted to see. I know we're doing matrix multiplication. She wanted attention, so we have to stop. And she's extremely jealous of the new 2 additions of the family. And she was a princess, and now she's just a common plebe, and she's not liking it. Bleeding the plebes. Now I'm going to do the second row of the outcome. I'm going to use this row vector and then go through the 4 columns for these entries. That's how my brain pieces this out. And then I do this as a secondary stage because now I've got the multiplication right and my brain doesn't have to worry about computing the numbers. And then once you've got the matrix multiplication right, then I'll go in and compute the numbers and give the final matrix. So here, 3 times 3 is 9 plus -1 times 1 is 8 now as a running total. You get used to doing this, and then, oh wait, where have I done this? This would be -1 times 4. And then 1 times -1. And that's how you don't get it wrong. This one and this one. Now I'm going to do this column. 3 times 1 plus -1 times 0 plus 1 times 3. The next one, 3 times 0 plus -1 times 1 plus 1 times 5. And then the last one, 3 times 2, -1 times 5, and 2 times 1. There, now I've got the matrix multiplication correctly. Now you'll see that this is where I always get it wrong. I like theoretical math. Computing numbers is something, I'm not an idiot savant. I don't know how to compute numbers, and this is really not going well for me a lot of the time. Compute slowly and now add the numbers up. Practical math. I like the theoretical stuff. This is how you compute matrix multiplication for any size. Now you have to go in there and actually get the numbers right. This is important too, a little bit. 6 plus 4 is 10. That's the first entry. This one is 2 and a 0 and a 0, so I get a 2. This one is a 0 and a 1 and a 0, so I get a 1. And this one is 4 plus 5 is 9. There's the first row of that outcome. What's my second row? My second row is going to be 9 minus 4 minus 1, so 9 minus 5 is 4. Here I'm going to get 3 plus 0 plus 3 is 6. Here I'm going to get 0 minus 1 plus 5 is 4. And here I'm going to get 6 minus 5 is 1 plus 2 is 3. There is how we do matrix multiplication. The size is 2 by 4. Let's do that again. All right, example 3, let A be 2, 3, 5, 7, the first 4 prime numbers. Let B be some arbitrary, I like to put zeros in there, so the computation will be nicer. I'll try to give you a 0. You're never getting zeros. And then C is this 3 by 3 matrix. The first thing you should do probably, and I didn't do it, I leave it off because I'm trying to trick you as if I'm going to give you this question. But the first thing you should do is put the size of them all 2 by 2, 2 by 3, 3 by 3. So even though we've listed 6, some of these we're not even going to have to compute. And that's nice. Coincidentally, this is all 6 permutations of comparing and making handshakes when the order matters, of A, B, B, A, C, C, A, and B, C, C, B. These are all the possible combinations. And this is where we see for real numbers, A times B is B times A. But we're going to see right now, this is matrix multiplication is not commutative. What that's going to say is A times B does not equal B times A. And I like these examples specifically because when they're not the same size, one isn't even defined. So how could they be equal to each other? Let's get to it. 1, A times B. 2 by 2 and 2 by 3. The inside indices match, and it will be a 2 by 3 matrix. It will be the same size as B when one of them is square. What does that say? Therefore, when I check this, I check to see whether I have to do anything. I do, so I write the actual matrices down. 2, 3, 5, 7. Matrix multiplied by 1, 2, 0, 3, 1, 4. You can write it here also if you want. 2 by 2, 2 by 3. The inside indices match, and it tells me now that my size is going to be 2 rows and 3 columns. So I'm going to want to leave myself a little bit of space to compute now, and that's why I'm doing that intermediately. If you can start doing this, you can start doing it and run the total in your head and just put the answer there. If you want to see me do that, let me try that for this one. Now what I'm doing is, because it's not too bad, it's 2 and 2. So it's just 2 pairs of numbers I have to add. For this entry, this is C11. So I have to do row 1 and column 1. This is 2 times 1 plus 3 times 3. So 9 plus 2 is 11 is the number I get there. If you don't like that, maybe I'll do it in the next one. What I'm doing is 2 times 1 plus 3 times 3. In this one, I'm doing, it'll be 2 plus 3, 2 plus 3 in the first row because I'm using this one. And then it should be 1, 3 here. And then what goes in these brackets? Here it's going to be 2, 1. Here it's going to be 0, 4. And then in the next row, what I'm going to do is it's going to be 5 plus 7, 5 plus 7, 5 plus 7. And then what goes in the brackets? The same numbers. 1, 3, 2, 1, 0, 4. Either way, there's matrix multiplication. What do I get? 11. 4 plus 3 is 7. 0 I like plus 12 is 12. Then we're going to get 5 plus 21 is 26. And 10 plus 7 is 17. And 0 plus 28 is 28. And this, just like we promised, is a 2 by 3 matrix. There's the matrix multiplication. For II, B times A, this is 2 by 3 and 2 by 2. The inside indices do not match. This is undefined. So this is what we're saying. Note, A times B does not equal B times A in general. This is not commutative operations. The order matters. You have to do it on the left when we get there, because you can't just put them on the right or switch them, because you're not allowed to flip them around like you are numbers. B times A doesn't even exist, so how could it equal A times B, which does exist? This is not a thing. Don't try flipping the order willy-nilly. Next, I think we only have to compute a couple of these, the rest don't work. 3, A times C. Again, this is 2 by 2, 3 by 3, undefined. Good. 1 before 5 is C times A. This is 3 by 3, this is 2 by 2. Didn't match, this is undefined. So you can't take two square matrices of different sizes and multiply them together, it'll never work. Now for 5 was B times C. This was 2 by 3 and 3 by 3. Oh, the inside indices match, and we're going to get a 2 by 3 matrix. So that again is going to give me, this is going to be 2 by 3. So this is what I set up first. I know the size, and then if you're not comfortable doing this, I have 2 rows and then 3 columns I have to compute entries with. I'll squeeze it in right here. B is 1, 2, 0, 3, 1, 4 times C, which is 1, 0, 1, 2, 1, 3, negative 1, 4, 0. And that's what we're going to multiply, so I can use my fingers. As soon as I do it, I'm like, oh, I haven't prepped myself so I can use my fingers correctly. So in the first row, again, I'm going to use the first row of A all the way across, and then just switch the columns that I use to get these entries. And then I'll switch to this row for the bottom row and go through the columns again. That's how I'm doing this. So it's this one times this one first. We'll go right here. So what is that? That's 1 times 1, 2 times 2, I don't care. 0 times negative 1, which will go away. Don't write it if you don't want. It won't add to the computation. So I gave myself zeros. Now what we're going to do is, the next one is going to be 0, I don't care, plus 2, and then plus 0, I don't care. And then in the next one, we're going to use this row in the last column, 1 times 1, plus 2 times 3, plus 0 times 0. And then in the next one, I'm going to now use this column, or this row, and then run through the columns. So this one times this one will be 3 times 1, plus 1 times 2, plus 4 times negative 1. This one times this column will be 3 times 0, plus 1 times 1, plus 4 times 4. And this row times the last column will give me 3 times 1, plus 1 times 3, plus 4 times I don't care. Those are all gone. And now I can simplify and put the entries in, or you can add these in your head if you really want, or you like to. Don't do that. Shortcuts make for long delays. This is 4 plus 1 is 5. This is 2. This is 7. This one is 5 minus 4 is 1. This one is going to give me 17. And this one is going to give me 6. This is matrix multiplication. C times A is 3 by 3 oh no, C times B, sorry. The last one I had to do, C times B, and this would be 2 by 3. Inside indices don't match, so undefined. In general, C times B does not equal B times C, and this one again is not even defined, but this is matrix multiplication. Let's do one last example, which is the one I should have done first possibly, but it'll recap and force you to watch the end of the video on my YouTube channel, and we'll give you the motivating example as to, again, why we define matrix multiplication the way we did. Not to torture first year students, this is just a good application. Let's see why we define multiplication this horrible way. All right, as in the last example, this is the motivation as to why we, after I make you do this a bunch of times, and you're probably cursing because I don't like matrix multiplication. I thought matrix addition was okay and scalar multiplication was okay, and then we ramp it way up for matrix multiplication. This isn't to make your life hell, even though it probably did. What the goal is, and what this motivation problem will show us, is we can now, once we have this machinery, thanks to these people who flesh out these horrible definitions for us, we can now view a linear system as matrix multiplication. We had to see how that worked first and be good at computing this. The goal is to now view this linear system as matrix multiplication in some way. So here it is. Given this linear 2 by 2 system, the coefficient matrix of that system is the matrix of coefficients. This guy, a 2 by 2 matrix. And then coincidentally, if we view this correctly, we can consider 2 column vectors, x1, x2, and then this guy, b1, b2. Most importantly, let's look at these two guys. And if we matrix multiply these two guys together, that gives us exactly the left-hand side of this system. What that tells us is a times x is 2 by 2 times 2 by 1. The inside indices match, and the outcome will also be 2 by 1. So what that gives us is, this is well defined, and that's going to be A11, A12, A21, A22, matrix multiplied by x1, x2. And that says I'm also going to get 2 by 1 matrix. And what are those? The first entry is this row multiplied by this row. So A11, x1 plus A12, x2. Oh, the first row. And what's this next row? This one is A21, x1 plus A22, x2. That row, the left-hand side of a linear system, is matrix multiplication of the coefficient matrix multiplied by the solution vector we're looking for. Therefore, what that says is, and then of course we're saying that equals B1, B2, which is also 2 by 1. And then we're saying that equals that. And when are two matrices equal? If and only if all their entries are equal. So then that says this has to equal this, and this has to equal this, and that's if and only if A11 x1 plus A12 x2 equals B1, and A21 x1 plus A22 x2 equals B2. Oh, the system I started with, I can now view my linear system as matrix multiplication. And then we're going to put this in shorthand and write this as AX equals B. What's your goal now? Solve for x, but this is matrix multiplication, so we are going to have to, how do I get rid of this? We're going to multiply by an inverse. Who's he? Well, first we're going to need the identity matrix. Well, who's that guy and how does that work? And then you're going to want A times A inverse equals identity, and then this is what the next video is going to be. We're going to define the identity matrix and the multiplicative inverse of a matrix for when that exists. And then we'll have to go into an extremely large tangent of determinants and determinant operations. And then once we get there, we'll give you a horrible formula for computing this thing. And then by then you'll have forgotten, you'll think you're a lumberjack again. I'm a lumberjack. It's like, yeah, we had to cut down trees to build houses. And then once we cut down all these trees and we're lumberjacks, we'll become architects as well and start building houses. Solve for X. I'll see you next time. Please subscribe and all that junk.